So in D monosaccharides, so I am going to discuss about the structure of D monosaccharides. D monosaccharides. Monosaccharides. As I told you before, in nature, right, monosaccharides exist as D. So I am going to discuss the structure of the D monosaccharides. Okay. Yeah. So the simplest D monosaccharide is this. That is CHO. Okay. Under D monosaccharide, I am going to discuss very specifically aldoses. Okay. Aldehyde containing monosaccharides. Okay. So this is the simplest monosaccharide we have, which consists of only one asymmetric carbon. Okay, in that asymmetric carbon, I'll put OH group in the right hand side. Okay, and here we have primary alcoholic group CH2OH. This is the simplest carbohydrate we have, and the name of this compound is D-glyceraldehyde. Glyceraldehyde. Okay, D-glyceraldehyde. Right now, this is a Aldo Tetros. Okay, because we have three carbon atoms here, one asymmetric carbon 2, and here we have one more carbon. So totally three carbon atoms are there. Therefore, it is an Aldo Tetros. Now we'll go to the next one, that is Aldo Tetros. So we have to introduce one more carbon here. If we introduce one more carbon, we'll get Aldo Tetros. Okay, so how to introduce? Yeah, let me do that here. So what I'm going to do, I'm going to introduce one more carbon here. Below aldehyde, I'm going to introduce. That is between the aldehyde carbon and the next carbon. Okay, so if I introduce CH2OH and we have HCHO, and this asymmetric carbon, okay, I keep it as such. Right, since in the here we have only one asymmetric carbon, and in that asymmetric carbon OH group is present in the right hand side, that's why it is called D. Okay, and see here I kept this CHOH as such. So this remains as D. Now in the new chiral carbon, I'll put OH group in the right hand side. Okay, and this compound is called Erythrolose. Okay, this compound is called Erythrolose. Similarly, what we can do, keep this CH2OH as such, keep the highest number asymmetric carbon in which OH group should be in right. Therefore, this is also D, and we have CHO at the terminal at the carbon number 1. Then in the newly introduced carbon, if we put OH group in left hand side, if I put OH group in right hand side, I'll get D-erythrose. If I put OH group in left hand side, I'll get D-triose. D-triose. Okay. From glyceraldehyde, this is 3 carbon containing aldose. So that's why it is called as Aldo Tetros. And these two are carbohydrates or aldoses containing 4 carbon atoms. So in 4 carbon atom, we have 2. One is D-erythrose, the other one is D-triose. Students, keep this in mind. Corresponding to D, we have L also. We have L. For L, you just replace this OH. You just shift these two groups. Put OH group in left hand side and hydrogen in the right hand side. You will get the corresponding L-triose. Okay. As I told you before, I am going to draw only D structures here. Okay. Now let me go to the next one. That is 5 carbon atom. Aldoses containing 5 carbon atom. So here I am going to introduce 2. Here I am going to introduce 2. The idea is this. What I am going to do, I am going to keep the entire structure as such. Between aldehyde carbon and the next carbon, I am going to introduce the new carbon here. Okay, the fifth, right, the new carbon I'm going to introduce here. Similarly, I'm going to introduce a new carbon here in such a manner that that new carbon may contain OH group in the right hand side or may contain OH group in the left hand side. So you'll get two isomers. Similarly here, the new carbon may contain OH group in the right hand side or left hand side. Okay, so let me draw in the next page. Yeah, see here in Erythrolose, right? I'll keep this structure as such, but what I'm going to do, CHO I'll keep it as such, CH2OH I'll keep it as such. Okay, and here we have already two carbon atoms are there. Let me keep them as such, HOH, HOH. Let me keep them as such. Right, now I'm going to introduce a new carbon here, new chiral carbon. In that new chiral carbon, if we put OH group in the right hand side, okay, this molecule, see, in the highest number chiral carbon, OH group is right, therefore it is D. Okay, and this compound is called D-ribose. D-ribose. Okay, suppose in the new chiral carbon, 1, 2, 3, CH2OH, I'll keep all these things as such. So these two chiral carbons are already there. Now in the new chiral carbon, if you put OH group in left hand side, okay, and see again in the terminal carbon or in the highest number asymmetry carbon, OH group is in the right hand side, therefore we should give D symbol. Okay, and this compound is called allose, D-arabinose, D-arabinose. Similarly here also I'm going to introduce a new carbon from 3-O's derivative. Let me draw here CHO. This is an easy method to draw the structures of monosaccharides. It's an easy method. Okay, so here see in this compound we have CHO at the terminal position and CH2OH in the other terminal position, and we have two chiral carbon already there. I'll keep them as such. So in the two chiral carbon HOH, H in the left hand side and the last carbon HOH. Okay, since in the highest number chiral carbon OH group is in the right hand side, I'll put D symbol. Okay, now in the new chiral carbon you put OH group in right. In the new chiral carbon you put OH group in the right. Okay, so this compound is called Xylose. Then next one, I'll keep the aldehyde group as such, CH2OH as such, right, and the terminal groups as such, right. Then in the new chiral carbon I'll put OH group in the left hand side, and this compound is called Lixose, right, and these four are aldoses containing 5 carbon atoms. So they are aldo pentoses. So under aldo pentose we have ribose, we have arabinose, we have xylose, and we have Lixose. Okay, how to remember the name? Yes, we have tricks here. Okay, so the first compound, see student, first compound starts with the letter G, and in tetros we have erythrose and 3-O's take the first letters E and T, so you'll get G-E-T, get, G-E-T, get. Okay, and here we have R-A-X-L, like Raxel. Okay, let me write like this. So get Raxel. Get Raxel. Okay, G for glyceraldehyde, E for erythrose, T 3-O's, R ribose, A arabinose, X xylose, and L Lixose. Just remember in this way. So you can remember all the monosaccharide structures. Okay, specifically aldoses. Right. Now let me go to the next one, that is See, these four aldoses contain 5 carbon atoms. Students, keep this in mind. We have corresponding L saccharides. I didn't draw here. For L saccharides, what you have to do? You just shift these two, that's all. Put OH group in left hand side, hydrogen right hand side. You will get L ribose. Similarly, you will get L arabinose, L xylose, L lixose. Okay, but I didn't do that. I am going to draw only D, because L is very simple, just opposite to that. Okay, right. So what I am going to do now? Now let me go to the 6 carbon variety. So here we have 2. Similarly, here we have 2. Here we have 2, and here we have 2. Okay, we have 8 isomers for okay, we have totally 8 isomers. What are they? Let me draw the structures here. CHO 1, 2, 3, 4, CH2 OH. So that totally 6 carbon atoms should be there. They are all Aldo Hexoses. Okay, CHO 6 carbon atom, 1, 2, 3, 4 chiral carbon and CH2OH. Similarly here CHO 1, 2, 3, 4 CH2OH. First I will draw like this, then I will put the groups in the right position. Okay. CHO, CH2OH, CHO, CH2OH, CHO, and the last one 1, 2, 3, 4 CH2OH and the terminal carbon containing aldehyde. Okay. Now what I am going to do, listen, let us start with the ribose first. Ribose. In ribose already we have 3 chiral carbon, keep them as such. Okay. So in the chiral carbon all the OH groups are in the right hand side, so I'll keep it as such, OH, OH, OH. Okay, and in the left hand side I'll put H. Right. In the new chiral carbon I'll put OH group in the right hand side in one isomer, and in the other isomer, this is from ribose, so I'll keep the 3 carbon as such. In the new carbon I'll put OH group in the left hand side. Okay, and this is called D-allose. Allose. Just remember all OH group in right hand side. Just remember like that. D-allose. Okay, and here only one OH group in left hand side. It is called D-altrose. Altered. Only one is altered. So just for remembering purpose I am saying like this. Altrose. Okay, this is allose and this is altrose. These two are obtained, okay, by introducing one carbon in ribose. Right. Similarly, you take arabinose. In arabinose, you introduce one carbon. Right. You will get these structures. Let me draw here. Keep these 3 groups chiral carbon configurations as such. HOH, HOH, and here HOH. Similarly, here also you should retain this. Okay, you should retain this structure as such. HOH, HOH. We should change only in the newly introduced chiral carbon. In one molecule, you put OH group in the right hand side. In the other molecule, you put OH group in the left hand side. Okay, and this molecule is called D-glucose. This is our glucose. Okay, this is glucose. Let me write here. And this molecule is called D-glucose. D-glucose. And this molecule is called D-mannose. D-mannose. D-glucose, D-mannose. Then from xylose we have 2. Let me keep the structure as such. H, OH, H, OH, H, OH. Similarly here H, OH, OH, H, H, OH. Very simple, you can draw in your own, but remembering the name is very, very important. And in the newly introduced chiral carbon, in one molecule you put OH group in the right hand side, in the other molecule you put OH group in the left hand side, and this is called Gulose, Gulose, G-U-L-O-S-E, Gulose. And this is called idose. Okay, this molecule is called idose. And for these two molecules, I'll keep the structure as such first. I'll keep the structure, this structure as such. So here 2 OH group left hand side, one is right. So let me write them as such: 2 OH group left, 1 OH group is in the right. Similarly, you keep them as such: H, OH, OH, H, OH, H, and H, OH. Okay, in the newly introduced chiral carbon, I'll put OH group right hand side in one molecule and left hand side in another molecule. Okay, and these two compounds, their names, let me write in a different color so that you can see clearly. This is called galactose, galactose, and this compound, I'll write the name here, talose, talose, O-S-E, talose. Okay, students, is this clear? Any doubt here? Any doubt? All these are monosaccharides or aldoses containing 6 carbon atoms. All are isomers. They have same molecular formula. They are all isomers. But okay, here we have 8 isomers. Corresponding DL is there, L. So 8 plus 8, you'll get 16 isomers. That's why I told you. In glucose, we have 16 optical isomers. These are the isomers actually. Right? Take 2.
Sir, what is the last compound?
Talose. D-talose. T-A-L-O-S-E, talose.
Okay, sir.
Okay. How to remember this name? Yes, for this also we have a shortcut. For this 7 compound, right? Glyceraldehyde, erythrose, triose, ribose, arabinose, xylose, and lixose. Remember this shortcut. Get Raxel. For these 8 compounds, yes, we have a shortcut. What is that? This is a standard shortcut which is used in many books. Okay, altruist, gladly make gum in gallon tanks. Okay, just remember this mnemonic. All altruists gladly make gum in gallon tank. What's meant by that? All means allose, the first compound. Okay, all means allose. Okay, altruist, alt means altros, allose, then altros. Okay, then gladly, GLA. Okay, I'm sorry, GL. You take the 2 letters, GL. GL means glucose, third one. Fourth one, mannose, no? So we have make. Here we have make, mannose. Then gum, GU. You take the first 2 letters, gulose. Then I for idose. Okay, I for idose here. Then GAL for galactose, and T for talose. Okay, students, is this clear? You just write and practice once. so that you'll get to know how to write this one. Okay, it's very simple one actually. You just have a practice in this, right? For remembering the name, okay, just keep this mnemonic in mind. All altruists gladly make gum in gallon tank. All means altros, I'm sorry, allose, de-allose. You just add the D letter in front. De-allose, de-altros, like that. Okay, so this is allose, altros, glucose, mannose, gulose, idose, galactose, talose. Okay, right. Now, and these are all the Aldo Hexoses we have. Okay, we have 6 D-Aldo Hexoses, right? Correspondingly, we have 8 D-Aldo Hexoses. Correspondingly, we have 8 L-Aldo Hexoses. Okay, so here I have given only the aldoses. Okay, we also have ketoses, right? Ketose molecules also there, right? Just take on this. Students, any doubt up to this? Any doubt?
No, sir.
Right, good. Now, let me go to the next one. For ketose, I'll give you the idea. I'll give you the name. Okay, you just proceed and find out all the structures. Okay, how to do that? Yeah. So let me take D monosaccharides. Okay, in ketosis. So we'll discuss the structures of D monosaccharide, which are all ketoses, right? That is ketose monosaccharides. Okay, yeah. So the simplest example is this, that is CH2OH. Then we have a keto group here, keto group. Then the third carbon containing chiral center, and here we have CH2OH. This is the simplest member of ketose, right? In ketose, this is the simplest member. We have a keto group here, and we have one chiral carbon. In that chiral carbon, OH group is in the right hand side, so it is called D, and this compound is called erythrolose. It is not erythrose. Don't confuse the name. Carefully write. Erythrolose. This is the simplest member. Since it contains 4 carbon, it is called Keto Tetros. It is a Keto Tetros. Okay, for ketose, the least member is the 4 carbon containing ketose. Okay, now what to do, students? How to write the keto pentose? If you want to write keto pentose, okay, it is very simple. You have to introduce the new carbon here between CO group and the next chiral center. Introduce a new chiral carbon here, and in one molecule put OH group in right hand side, in the other molecule you put OH group in left hand side. You just try it, okay? And here, if you put OH group in right hand side, you will get what is called D-ribulose. Ribulose. If you put OH group in left hand side, you will get Xylulose. This is very, very important for JEE preparation. Okay, so keep all these things in mind. D-ribulose and D-xylulose. Okay, these two are ketoses containing 5 carbon atoms. So they are ketopentoses. So in ketopentose we have 2. Okay, and remember I have given only D, so correspondingly we have L. Okay, then the next one. Students, I didn't draw that structure. You try it, okay? You try to do that. Will you do, students? You have to introduce the new chiral center between the keto group and the next chiral center, next immediate chiral center. Okay, now what I'm going to do, from D ribulose you introduce one more chiral center, from D xylulose you introduce one more chiral center, so you'll get ketosis containing 6 carbon atoms. You'll get keto hexoses. In keto hexose we have 4. Okay, what are they? D psychose, then D fructose, D psychose and D fructose, then D sorbose, D sorbose, and D tagatose, T-A-G-A, tagatose. Okay, D psychose, D fructose. Fructose is very important for us because in NCRT, right, we have fructose. So keep this in mind, very, very important, fructose. All these are ketoses, right? All these are ketoses. So this is Keto Tetros, and these 2 are Keto Pentose, and these 4 are Keto Hexoses. Okay, I didn't draw the structure. I'll just leave it to you. You try and get experience in drawing the structure. Okay. Right. Now, so now you know how to draw the structures of the monosaccharides. Okay. Now what I'm going to do, I'll introduce the next important one called Epimers. Okay. In carbohydrate, this particular isomers are very, very important, Epimers. Often you can expect questions from this, right? Epimers. But to understand Epimers, you must know these 2 things. Okay, listen, we classify stereoisomers into 2. We classify stereoisomers into 2, right? What are they? Number 1, enantiomers. Number 2, diastereomers. Students, keep this in mind, very, very important. Stereoisomers means, okay, 2 molecules, suppose you take 2 molecules, they have same molecular formula, same structure. Stereoisomers means, okay, molecular formula same, okay, you take 2 compounds if they have same molecular formula. And number 2, structure also same. Okay, all the groups are arranged in a proper position, they have same molecular formula, they have same structure, they have same functional group. Okay, everything same, right? I'm sorry, they have same molecular formula and same structure. Then third one is very important, that is so they have same functional group also same functional group. If one contain aldehyde, the other should contain also aldehyde, right? They differ, very important, they have same molecular formula, same structure, same functional group, everything. They differ only in the spatial orientation, the arrangement of groups, okay, about the carbon atom, right? Spatial orientation, they have spatial orientation, right? In space, how the groups are oriented, that is different. They have different spatial orientation. So if 2 molecules, they have same molecular formula, same structure, same functional group, but they have different spatial orientation. We call them as stereoisomers. In stereoisomers, we have enantiomers and diastereomers. What are enantiomers? If the two molecules, I'll take molecule 1 and molecule 2, they obey all these formula, they have same structure, everything. If they have object and mirror image relationship, okay, if you take one molecule as object and draw the mirror image will appear like the second molecule. If the two molecules have object and mirror image relationship, we call them as enantiomers. So what are enantiomers? Enantiomers are stereoisomers. I repeat, enantiomers are stereoisomers. Okay, they have object and mirror image relationship. They have object and mirror image relationship. What are diastereomers? Diastereomers are also stereoisomers, but they do not have object and mirror image. Okay, if you draw right, they do not have object and mirror image relationship. That's all. That's the difference. Students, is this clear? Any doubt in this? What are stereoisomers? Stereoisomers have same molecular formula, same structure, same functional group, but the spatial orientation of atoms or groups, right, about a carbon atom, right, or one or two carbon atom, right, may be different. So if spatial orientations are different, then those two molecules are called as stereoisomers. In stereoisomers, we have two, enantiomers and diastereomers. What are enantiomers? If the two molecules have object and mirror image relationship, we call them as enantiomers. If the two molecules do not have object and mirror image relationship, we call them as diastereomers. Okay, so very simple one, but very essential to keep in mind. Okay, enantiomers, you cannot separate them. Okay, it's very tough task to separate, right? We can separate, but it is very difficult to separate, very difficult. Enantiomers. Whereas diastereomers, okay, in diastereomers, M1 and M2, they have some difference in the physical property. In enantiomer, molecule 1, molecule 2, both these molecules have same physical property, same chemical property. Very difficult to separate them. But we can, but very difficult. Whereas in the case of diastereomers, the molecule 1 and molecule 2, okay, they differ in some physical properties. Therefore, we can easily separate them. Okay, so diastereomers can suppose if you have mixture of M1 and M2, yes, it is very easy to separate. But if you have mixture of M1, M2 of enantiomers, it is very difficult. Okay, keep this in mind. Now what I am going to do is let me come to epimers. What are epimers? Students, is this clear? Any doubt in this?
No, sir.
Okay, right. Now let me come to epimers. What are epimers? Right here. What are epimers? Epimers are diastereomers. Right? What are epimers? Epimers are diastereomers. Epimers are diastereomers. They do not have object and mirror image relationship. Epimers are diastereomers. Okay, epimers are diastereomers and they differ epimers are diastereomers which differ in the configuration, of only one chiral center. Only one chiral center or asymmetric center. Only one chiral carbon. Let me write like this. Epimers are diastereomers which differ in the configuration of only one chiral carbon or chiral center or chiral center. Okay, this is the definition of epimers. Epimers are diastereomers. Diastereo means they do not have object and mirror image relationship. They are diastereomers. Okay, epimers are diastereomers which differ in the configuration of only one chiral carbon atom, which differ in the configuration of only one chiral carbon. Okay, yeah. See, I'll show you an example. Say for I'll take glucose. See the structure of glucose. Glucose contains 4 chiral center, CH2OH, and let me show the arrangement. First carbon OH group, second carbon OH group in the left hand side, third carbon OH group in the left hand side, fourth carbon OH group in the right hand side, and fifth carbon OH group in the right hand side. This is the Fischer projection of glucose, D-glucose. This is D-glucose. Okay. Now what I'm going to do, I'll draw one isomer. See this one? This is an isomer. CHO, CH2OH, HOH, 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 and HOH. And this compound is called D-mannose. Mannose. D-glucose and D-mannose. Students, see these two compounds. These two compounds, see the chiral centers. This chiral center, yes, OH group right, OH group right. Then the next chiral center, OH group right, OH group right. The next chiral center, OH group left, OH group left. So up to this, everything is same. Whereas see this chiral center, okay, in this molecule, the OH group is in the right hand side, whereas here the OH group is in the left hand side. So they differ only in one chiral center, am I right? All chiral centers have same configuration, but only in this chiral center the configurations are different. Okay, so D-glucose and D-mannose, they are epimers. They are epimers. In which carbon atom they differ, students? In which carbon atom they differ? This is carbon number 1, carbon number 2, right? At carbon number 2. Therefore, we call them as C2 epimers. C2 epimers, which means they differ in carbon number 2. Right? So, D-glucose and D-mannose are C2 epimers. Now, I'll give you another structure so that you will get a little more clarity here. So, let me give another compound. CHO, CH2OH, okay, HOH, 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 HOH. Now, this compound is called D-galactose. Galactose. Okay, students, compare glucose and galactose. Compare the structure of glucose and galactose. In which carbon they differ? See the structure of glucose and see the structure of galactose.
Fourth carbon, sir.
Okay, in fourth carbon, right? You're right. So in fourth carbon, here we have OH group in the right hand side, whereas here in the fourth carbon, OH group is the left hand side. Therefore, we can say D-glucose and D-galactose are C4 epimers. Okay, let me write in the next page. Okay, let me write in the next page. See what I'm trying to say. D-glucose and D-mannose, these two are C2 epimers. Okay, whereas D-glucose and D-galactose are C4 epimers. Okay, students, what about D-mannose and D-galactose. Can you tell me? Others, turn on your camera. Hello students, turn on your camera. Yeah. Just compare the two structures, mannose and galactose. In which carbon they differ?
Second and fourth, sir.
So if they differ in two carbon atom, they are not epimers. That's the point. Okay, if two isomers, right? If two Aldo Hexoses or Aldo Pentoses, whatever it is, same family should be there. Okay, if they differ only in one chiral center, then we can call them as epimers. So here glucose and mannose are C2 epimers. Glucose and galactose are C4 epimers. Mannose and galactose are not epimers because they differ in two carbon atoms. They are not epimers. Okay, is this clear, student? Any doubt here? Any doubt?
No, sir.
Okay, ma, right, take down. Now I'll give you one important information here. This is very important for JEE as well as NEET. Okay, what is that? See, among in Aldo Hexoses, what are all the compounds we have in Aldo Hexose, students? Let me write like this. So this is not Fisher projection. This is I am giving you just for understanding purpose. Aldo Hexoses. Can you give the names of Aldo Hexoses? Altrose, allose, correct? All OH group in right hand side. Allose. Let me put the symbol A. Allose, altrose. This here represent allose and this here represent altrose. Then glucose, mannose. Then gulose, gulose and idose. Then galactose and talose. Correct? These are the D monosaccharides we saw. Okay, D as well as L also there, but I'm not going to do that. So this here represent allose and this here represent altrose. Glucose, mannose, gulose, idose, galactose and talose. Okay, I have taken Aldo Hexoses. Students, listen carefully. Allose and altrose, they are C2 epimers. Glucose and mannose, C2 epimers. Gulose and idose, C2 epimers. Galactose and talose, they are C2 epimers. They are all C2. These two, right? C2 epimers. So whatever may be the question, you can easily answer. Allose, altrose, C2 epimers. Glucose and mannose are C2 epimers. Gulose and idose are C2 epimers. Galactose and talose are C2 epimers. Okay, then students, observe carefully. Now I'll take allose and glucose. Allose and glucose, they are C3 epimers. Gulose and galactose, they are again C3 epimers. Okay, similarly here altrose and mannose are C3 epimers. Idose and talose are C3 epimers. Students, is this clear? Any doubt? It is a simple trick to remember the possible epimers of Aldo Hexose. Okay, allose, altrose, these are all C2. These are all C2 epimers. C2. Then take this first one and the second one. These two are C3. Similarly, these two are C3. Third and fourth. Similarly here, 1, 2, C3, 3, 4, C3. Now, in the same structure, I will show this one. Take 1 and 3. Students, see this carefully. I am taking 1 and 3. 1 and 3 are C4 epimers. Similarly, 2 and 4 are C4 epimers. Is this clear, student? Am I confusing you? Is it clear?
Yes, sir.
Yeah, take note. See, these pairs are C2 epimers, these pairs. Here in the left hand side, 1, 2 are C3, 3 and 4 are C3. 1 and 3 are C4 epimers, 2 and 4 are C4 epimers. Okay. Similarly here, 1 and 3 are C4 epimers. Okay, 2 and 4 are C4 epimers. Very simple. Very simple. If you remember this, okay, you can answer any questions in JEE based on epimers. Okay. Here I have taken Aldo Hexoses. Okay, I have taken only Aldo Hexoses. Similarly, you can take Aldo Pentose. Aldo Pentose. Let me write here Aldo Pentose. In Aldo Pentose, yeah, I'll take the molecules like this. This is in Aldo Pentose we have ribulose, right? I'm sorry, we have ribose, we have arabinose, then we have xylose. I'll put X, xylose and lexose, Raxel, R-A-X-L, Raxel. These are all aldopentoses. Okay, and remember ribose and arabinose. They are C2 epimers. Okay, ribose. These two are C2 epimers. Similarly, xylose and lexose. They are also C2 epimers. Okay, they are C2 epimers. They differ only in one chiral center. And these two, 1 and 2, are C3. Similarly, here also they are C3 epimers. Is this clear, student?
Yes, sir.
Yes. If you write like this,
Yes,
you can answer any compound. Okay. Whatever JEE question, whatever NEET question they ask from epimers, you can easily answer. Remember this idea. Okay. Is this clear, student? Any doubt?
No doubts.
Right, ma. Good. Now, in ketosis, there is a small difference. So let me just tell you that. I'll take Keto Hexoses. In Keto Hexoses, there is a small difference. What is that? Okay, in Keto Hexoses, we have only 4 members. Okay, Cyclose and fructose, okay, sorbose and tagatose. I have taken Keto Hexoses family, Cyclose, fructose, sorbose and tagatose. Okay, students, see here there is a small difference. Here in all these compounds, C2 contain carbonyl group. It is not a chiral Ka center. So there won't be any C2I epimers here. See all the Keto Hexoses, right? If you see all the Keto Hexoses, second carbon contain carbonyl group, keto group. Only in third, fourth carbon, fifth carbon we have chiral carbon. Therefore, in Keto Hexoses, you will never have C2 epimers. Right? So here, this Cyclose and fructose, these two are C3 epimers. These two pairs are C3 and these two pairs also C3. Cyclose and sorbose are C4 epimers. Simple, C4. and these two are C4. Very easy. Only one thing you should keep in mind: in keto hexose, C2 epimers, okay, in keto hexoses, C2 epimers do not exist. Okay, only C3 and C4 are there. This is cyclose and this is fructose, this is sorbose and this is tagatose. Okay, yeah, so I have given the structures and one important isomer called epimers. Okay, now what I'm going to do, I will show you another important one, cyclic structure. Okay, cyclic structure of monosaccharides. Cyclic structure of monosaccharides. Okay, cyclic structure of monosaccharide, very important. Students, remember, whenever aldoses or ketoses containing more than 4 carbon atoms, see, let me write here, if number of carbon atom is more than 4, number of carbon atoms, if number of carbon atoms is more than 4, okay, then the molecule, right, exists in cyclic structures also, in cyclic structure. Okay, if the number of carbon atom is more than 4, that is aldo pentose, aldo hexose, keto pentose, keto hexose, right? If number of carbon atom is more than 4, then those molecules can also exist in cyclic structure. Okay, now just for understanding purpose, I am going to take glucose. I'll take glucose, D-glucose, right? I'm going to take D-glucose just for understanding the cyclic structure. Then I'll show you how to draw a cyclic structure for D-fructose, right? And if you want, you can draw other structures also. Okay. Now, first let me show you the open chain structure of glucose. This is called open chain structure. CHO containing 5 chiral center and 4 chiral center and a primary alcoholic group at the terminal position. And here first in the second carbon, OH group should be in the right hand side in glucose. In third carbon, OH group should be in the left hand side. Remember, these are all proper structures of carbohydrate. Okay, proper structure of carbohydrate. So keep this in mind. It's a proper structure of carbohydrate, glucose. Okay, and this is called open chain structure. Whatever that I have drawn here is open chain structure. Now I am going to convert this into cyclic. Okay, how to convert this into cyclic? See what I am going to do. I am going to write. See, this is carbon number 1, 2, 3, 4, 5, 6. I am going to write the structure like this. See, we have aldehyde group, C double bond OH. Okay, this is carbon number 1. Then carbon number 2, carbon number 3, carbon number 4, carbon number 5. Okay, and carbon number 6, let me show separately. Okay, this is carbon number 6. Carbon number 6 contain CH2OH group. I'll show it separately. Okay, then in carbon number 5, students, we have OH group, right? I'll show the OH group like this. This is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. This is carbon 6. In carbon number 5, we have a OH group. Students, this is very, very important. If we have OH group and aldehyde group in a molecule, okay, there is a possibility of forming cyclic structure due to the internal nucleophilic attack. What is internal nucleophilic attack? We will understand this, okay, as we go along. Now what will happen? See, this oxygen has a lone pair. Okay, using that lone pair, it will attack this carbonyl group. It will attack the carbonyl group so that in the double bond, one bond will shift to oxygen. Okay, in double bond, you know very well, in double bond, one bond is sigma, the other one is pi. When lone pair attacks this carbon, the pi bond shifts to oxygen, so oxygen will get minus charge. Oxygen will get minus charge. And here, since this oxygen donate the lone pair and attacks, this oxygen become positive. To neutralize that positive charge, this hydrogen comes out as H+. Okay, this oxygen donates the lone pair so that the oxygen become plus. To neutralize that positive charge, this hydrogen comes out as H+, so that oxygen get neutralized. So what will I get? And that H+ get attached with this O. Okay, so what will I get? I'll show here. So we have carbon number 1. Now it will contain a OH group. This carbon 1 now, the pi bond shifts here, you'll get O minus, then the O minus takes this H plus, you'll get COH. This is carbon number 1, this is carbon number 2, carbon number 3, carbon number 4, carbon number 5, and here we have oxygen atom. Carbon number 6 is there separately. This oxygen atom now forms a bond with the carbon number 1, so that you will get a cyclic structure. Student, remember, this OH group is called alcohol group, and this is aldehyde group. When alcohol and aldehyde reacts, students, keep this in mind, very very important. When alcohol and aldehyde react, you will get a compound called hemiacetal. Hemiacetal. So this compound is called hemiacetal. When alcohol reacts with aldehyde, okay, you will get a structure like this. Let me just show like this. You will get RO. This is from alcohol, and this is from aldehyde. Okay, you will get a structure like this. Right? This structure is what we call as hemiacetal. Okay, here we have oxygen. The next carbon has OH group. This is called hemiacetal. And since we have cyclic structure, it is called cyclic hemiacetal. Cyclic hemiacetal. Is this clear, student? Why this cyclic structure is formed? Because this molecule consists of 6 carbon atoms. I have told you, if you have more than 4 carbon, then the molecule can form cyclic structures. Okay, right. Students, I stop here. In the next class, we'll discuss the actual way of drawing the cyclic structure. Okay, we have 2 projections. We have 2 methods of drawing cyclic structure. We'll discuss that in the next class. Okay, I stop here.
Thank you, sir.